Earth system models are our primary tools for predicting global climate, but strict computational limits force us to run them at coarse resolutions. These resolutions introduce systematic physical biases. Over time, mathematical approximations accumulate, and the simulation drifts away from observed reality. The computational cost of fixing this is staggering. Because of cubic scaling in three-dimensional space and time, refining a model's grid from 100 kilometers to 25 kilometers demands 64 times more processing power. We can bypass this barrier by retrofitting legacy models with an online bias correction, a machine learning operator that runs during the simulation to adjust the physics. This correction targets specific atmospheric state variables at every step: zonal wind, meridional wind, temperature, and specific humidity. Addressing this drift is a trade-off between physical fidelity and the reality of a finite compute budget. It is a problem of computational economics that requires a hybrid architecture. To train this hybrid architecture, we use a process called nudging. During a controlled simulation, the coarse model is constantly pulled toward high-fidelity historical reference data from the ERA5 global reanalysis. This constant pulling generates a discrete, measurable mathematical force at every time step, known as the nudging tendency. This heat map reveals the global spatial variations of these corrective forces. Note the distinct horizontal zonal bands where the strongest corrections are concentrated. Instead of manually tuning the underlying physics engine, we treat the nudging tendency itself as a supervised learning target for a neural network. In the offline training phase, the network learns from the ERA5 reference data. Once deployed online, the reference data is removed, and the trained model predicts the required corrections autonomously. By predicting the exact force needed to align the model with historical data, we convert a manual assimilation process into an automated, deployable ML operator. Integrating this operator into legacy systems like the E3SM climate model requires working within strict limits. The model runs on CPUs and only exposes the immediate previous time step, ruling out heavy, history-dependent recurrent models. Given these constraints, an image-to-image UNet serves as the logical baseline architecture. However, a raw UNet struggles to perform. Without knowing geographic context, like land fractions or latitude, its prediction accuracy is significantly reduced. We solve this using feature-wise linear modulation, or film. As shown, an embedding block generates parameters conditioning the network's branches. This mechanism applies a transformation, gamma 0 f plus beta 0, at every depth, allowing the network to modulate atmospheric predictions based on the terrain below. Adding film conditioning triples the pattern correlation for wind predictions without adding significant computational overhead. In physical modeling, abstract spatial patterns are insufficient. These networks must be mathematically anchored to geographic reality at every processing depth. Standard UNets also face a structural issue called rank collapse. When upsampling data through a single operator, the network loses critical fine-resolution atmospheric details. The first proposed solution is IUNet, which replaces standard sequential convolutions with parallel inception branches. These parallel structures allow the network to capture fine, medium, and coarse spatial patterns simultaneously. The second, more advanced solution is the M&M architecture, which completely redesigns the upsampling decoder. M&M avoids rank collapse by utilizing three complementary upsampling pathways: transposed convolution, interpolation, and pixel shuffle, which recombine to form a dense, high-resolution grid. Preventing information loss requires structural diversity in the network pathways, rather than simply adding more parameters to a standard design. We validate these architectures offline using out-of-year data from 2015, testing their ability to track weather patterns the network never saw during training. We compare these models against a UNet that was simply scaled up to match their 6.7 million parameters. Mere parameter scaling yields minimal accuracy gains. This chart tracks temporal correlation for zonal wind across vertical layers. The red dashed line shows the M&M architecture maintaining high positive values. Contrast this with the blue dashed line for the baseline UNet, which oscillates wildly and plunges below the zero line into negative territory. These negative values represent severe temporal misalignment. At those altitudes, the model is predicting the exact opposite of the actual atmospheric physics. In Earth system modeling, architectural expressiveness, how the network is structured, strictly overrides parameter mass. The ultimate test is a live deployment. We coupled these PyTorch models inside the Fortran-based climate model for a 5-year free-running simulation. We used TorchScript to bind the modern machine learning operators directly into the legacy dynamical core. Both IUNet and M&M stably reduce global errors by 2 to 10% across key thermodynamic fields over the 5-year run. The parameter-heavy UNet failed this test. Its lack of structural expressiveness created compounding feedback loops that actively degraded the simulation. There are limits to this framework. Because the models only trained on a 2-year window, they struggle to correct extreme out-of-distribution events like the 2015 El Niño. Theoretical offline accuracy is meaningless if a model's inductive biases cannot survive the continuous, compounding feedback of a live physical simulation. We must also consider computational reality. Integrating machine learning necessarily slows down the baseline physics simulation. This chart compares the simulated years per day, or SYPD. The baseline physics model reaches 12.7 years per day, while the ML augmented models range from 1.3 to 8.5. While the hybrid model is roughly 1.5 to 10 times slower than the baseline, it is still far more efficient than the 64-fold compute increase required to achieve similar accuracy through pure physics. This framework occupies a deliberate middle ground on the modeling spectrum, positioned between legacy physics models and experimental pure machine learning layers. This proves that stable, multi-year machine learning integration inside legacy climate solvers is computationally feasible today, providing a scalable bridge to the future of Earth system modeling.